Hello everyone, my name is Qiang and I'm from Biomedia Group at Imperial College London. Today I will talk about PialNN, a fast deep learning framework for cortical pale surface reconstruction. Given a brain MRI image, cortical surface reconstruction aims to extract the inner and outer surfaces of the cerebral cortex, which are also called white matter surface and pale surface. As the cerebral cortex is highly convoluted and folded, it is challenging to extract a geometrically accurate surface. In addition, the cortical surfaces should be topologically equivalent to a sphere and have no self-intersections. Another challenge is the efficiency, as the traditional approaches are usually time-consuming. Here is the cortical surface reconstruction pipeline of FreeSurfer, which is a widely used neural image analysis tool. It takes around 4 hours to reconstruct the cortical surfaces of a single subject. Such a pipeline is time-consuming, and therefore, we need an efficient alternative approach. In this work, we take the first step and focus on the pale surface reconstruction. Instead of iteratively expanding and self-intersections checking, we consider deep learning approaches, which provide a fast and end-to-end solution. The existing deep learning methods for cortical surface reconstruction can be divided into implicit and explicit methods. The implicit methods include FastSurfer and DeepCSR. These methods usually learn a deep neural network to predict the segmentations or other implicit representations, such as the sun distance function. Then the surface mesh is extracted by matching cubes algorithm. However, a topology correction algorithm should be applied to fix the topology of the surfaces, which is computationally expensive. In contrast, the explicit methods, such as voxel mesh, are fast and require no topology correction. Given an initial surface with a spherical topology, the neural network learns to deform it to a target surface end-to-end. Several surface-based regularization terms are usually used in the loss function to improve the mesh quality. In this work, we propose a deep learning approach which is called Pial Neural Network. The Pial Neural Network is designed based on the explicit methods. It is fast and it deforms an initial white matter surface iteratively to a pale surface in 1 second. So given an input surface mesh, we concatenate the coordinates and the normal of each vertex. Then we use a multi-layer perceptron to extract the point feature from each vertex. Furthermore, we want to capture the neighborhood information of each vertex in the brain MRI volume. Here we introduce a local convolution method. As shown in the right figure, we first build an image pyramid based on the input MRI and capture the multi-scale information. For each vertex, we find its corresponding position in the image pyramid and extract its neighborhood voxels at the 3D cubes with length k. We call this procedure as cube sampling. Next, we use a convolutional layer with kernel set k on all the cubes. So now each vertex has a feature vector containing its neighborhood information. An MLP layer is then followed to extract the local feature. Such local convolution method is memory efficient, as we do not need to run convolutional operation on the entire 3D MRI volume. The complexity only relies on the number of the vertices. Now we can concatenate the point feature and the local feature, and use several dense layers to predict the displacement or translation of each vertex. Then we have an output surface mesh by adding the displacement to the original coordinates. So this is one of the deformation blocks. The overall PialNN architecture actually employs 3 deformation blocks. A differentiable Ablation smooth layer is used to reduce the self-intersections. Our architecture is lightweight and memory efficient, which allows us to process high-resolution mesh data with 150,000 vertices, and it only requires less than 10 GB GPU memory. For the training of a Pial neural network, we'll assume that the inner and outer surfaces meshes has the same connectivity, which means the predicted surfaces also have the same connectivity at the ground truth. This can be easily achieved if the training surfaces are generated by FreeSurfer. Therefore, based on this point-to-point correspondence, we can simply compute the mean squared loss without additional point matching. This loss function provides a strong supervision, and each vertex can learn to move to a correct position. So we do not need any surface-based regularization terms. In our experiments, we use HCP young adult dataset. The brain MRI is clipped to a suitable site with 1 mm resolution. Here are some example data. The white matter and pale surfaces are generated by FreeSurfer. In the training phase, the generated white matter surfaces are used as the input, and the pale surfaces are used as ground truth. In the testing phase, the initial white matter surfaces can be generated by other faster approaches. So this is the results of the experiments. The top figures are the predicted pale surfaces, and the bottom ones are the results of FreeSurfer. We can see that the PialNN results is very similar to FreeSurfer and even has a better measure quality. The left figure provides the comparison of our framework with other state-of-the-art deep learning baselines, such as voxel mesh and deep CSR. The result shows that the voxel mesh tends to oversmooth the surface, and the deep CSR sometimes fail to distinguish two close gyrus regions. For the runtime shown in the right figure, the PialNN can predict the pale surface of both hemispheres within 1 second, whereas the voxel mesh needs 5 seconds because the input mesh should be downsampled. The deep CSR takes 2 minutes due to the time-consuming topology correction algorithm, and FreeSurfer takes around 10 minutes for pale surface reconstruction. For the evaluation, we use 3 distance-based metrics to compute the distance between the predicted surface and the FreeSurfer ground truth. This table reports the geometric error of the reconstruction using different methods. The low score means better result. It demonstrates that the PialNN framework achieves the best performance. It reduces the geometric error by 30% compared to other baselines. The bottom figure shows the contour of the pale surface projected on the brain MRI volume. It shows that the PialNN achieves the best reconstruction in the 4 highlighted areas. We also conducted 3 ablation studies. Just recall that the local convolution method employs cube sampling to extract voxel cubes from multi-scale input MRI. Here we consider point sampling, which only extract a single voxel point, and we also consider single-scale input. The results indicate that the cube sampling is important for our architecture. In addition, we have also tried to replace the MLP layers with graph convolutional neural network, but the results are not improved. In conclusion, the proposed PialNN framework is accurate, fast, and memory efficient, which reduces 30% geometric error and predicts a high-resolution pale surface within 1 second. However, there are 2 limitations of the proposed framework. First, as we only consider the pale surface reconstruction, the initial white matter surface is generated by FreeSurfer, which is still time-consuming. Second, although we use Laplacian smooth to reduce the self-intersections, there are no hard constraints on this problem. The future work will focus on the deep learning method for white matter surface reconstruction and theoretically prevent the self-intersections. We already have some preliminary results. Please see our follow-up work if you are interested in this topic. Finally, I would like to thank my co-authors for their support and help, and thank you for listening.